We begin module 2 of lecture 2. So the overall steps are as follows. In step 1, we decompose the system into basic blocks and generate the master controller. So what do we have here? And what do we have? We said that we have a set of concurrent communicating processes, and each of these modules will be a code. Now this code will have a control and data flow graph. So what we are saying here, each module is parsed and its flow graph is extracted. So if I have a program, if I have a high level language or hardware description language program, I can extract the flow graph or the flow chart out of it, right? Now given this flow chart, from this flow chart, it is easy to obtain the control flow graph of the application. Now what is the control flow graph of this program? In this, each node of this graph will be a basic block, and the edges will define the dependencies between these basic blocks, right? So what is a basic block? A basic block is a piece of sequential or straight line code which has a single entry point and a single exit point. So therefore, a basic block is a piece of code which does not contain conditions or loops inside it, which means that the program control will never come to some point which is inside this basic block. So the control will come only at the beginning of the basic block, and control, there will be a sequential straight line code set of statements. Control will flow from one statement to another in sequence through the basic block and come out of this sequence. Okay, so neither can control go out in between this basic block somewhere, neither can control come inside the basic block within a set of statements, right? So this is the definition of a basic block. Given this control flow graph, we generate the master controller. So basically, the master controller has a one-to-one correspondence with the control flow graph. So the states of this master controller, the master controller FSM, will be the nodes of the control flow graph, and the transitions will be the edges of the control flow graph, right? So now we take an example to show it. Let us say that we have a code like this: w equals to 0, x equals to x plus y, y equals to 0. If x greater than z, then y equals to x, x plus plus, else y equals to z, z plus plus, and at the end w equals to x plus y. So we see that what are the pieces of straight line code we have here. First, we start with w equals to 0. There are no conditions or loops. X equals to x plus y, y equals to 0, and the if statement. The statement if will always, so once we enter this block, there is no way in which the if statement will not be executed. So the if statement will be part of the first basic block, right? Because there is no chance that I will not execute the if statement and the control will flow outside the first basic block. So therefore, the if statement will be part of the first basic block. Now, if the condition is true, we go to the second basic block, y equals to x, x plus plus. If this condition is false, we go to the third basic block, y equals to z, z plus, y equals to z and z plus plus, and then we have a fifth basic block, w equals to x plus y. So we see that these are the maximal pieces of straight line code that are possible from this program. And then each of these basic blocks, so this is basic block 1, this is basic block 2, this is basic block 3, and this is basic block 4. Okay, so we have an entry point. So another important point here is that a CFG is polar in the sense that it has a single entry point and a single exit point, a source and a sink. So it enters through the first, it enters and then comes into the first basic block. If it is true, it executes B2. If it is false, it executes B3. And the condition here, if it is true or false, and then it executes B4 and finally exits. Okay, So this is how a control flow graph looks. Now, given this control flow graph, we said that we can obtain the master controller. So what will this master controller control? How and when should each basic block be activated, right? However, we said that the master controller is very similar to the control flow graph, but it's not exactly the control flow graph. Why did we say that? Because we cannot ascribe timing information to the master controller until we have ascribed timing information to the basic blocks themselves. So after we have ascribed timing information to the basic blocks themselves, we can ascribe timing information and then it becomes a full-fledged controller. So therefore, before we can generate the final master controller, we have to first look inside each basic block. So let us therefore take a look what happens within a basic block. Now, what we have to do is we have to schedule the operations within a basic block. So then what is a basic block? If you see, we will see that a basic block has no control or loops inside it. So therefore, it only contains a set of paths for data to flow. So control data will go into at the beginning of this basic block. Data will enter, input data will enter. These input data will go through a series of transformations because of the combinational operations. It's not sequential. Why? Because there are no controls, no loops. So ideally, all the operations are combinational operations. So the data flows through these set of combinational operations and comes out at the end of the basic block. So what we understand is that the basic block therefore can be represented through a data flow graph. The entire application module as such is therefore a control and data flow graph. The control flow graph represents what? The nodes represent the basic blocks and the connections between the basic blocks, and each basic block is in itself a data flow graph. So the whole combined graph that we get is actually a control and data flow graph. It's a hierarchical structure that we are looking at. Right. Now, because there are only combinational components inside a basic block, we can very well understand that all operations within a basic block in principle can be performed within a single clock cycle. Why? Because let us, if we go into the previous basic block, here w equals to 0, x equals to x plus y, y equals to 0, and this if x greater than z, this x greater than z computation, we see that there is no controller loop inside it. So data enters, everything cannot be done in parallel, it has to be done in sequence, but there is no time, we don't need time to explicitly pass in between them. In a single clock step, I can do all these operations together. However, if we have many operations within a single clock step, the problem is that it will lead to unacceptable hardware cost and delays. Why hardware cost? Let us say we have four comparison operations within a basic block. Now all this, because it is in a single clock step, I cannot reuse this comparison at the comparison operator at different clock steps. All these comparison operations have to be executed on different comparator units. If I assume that I have comparator hardware resources, so it has to be executed using different comparator hardware units because all is being done at a single clock step. So likewise, for all different types of operations, all has to be given separate operators or functional units to execute, and therefore it will lead to unacceptable hardware costs because of this reduced resource sharing that we have. When we divide things into different time steps, what happens is that I can share the same resource at different time steps, which is not possible if I do it within a single clock step. Right? And also, it will also increase delay. Why? Let us say this clock is not only feeding this basic block here, this clock is possibly feeding many other basic blocks in different parts of the in this module, maybe within this module and in other modules of the whole application. So therefore all these applications will have to incur this delay, and there could be there could be very small basic blocks as well. All basic blocks will not be this big. So all small basic blocks, because we have said that all operations within a basic block will have only one clock step, we will execute whatever be the size of the basic block, small or big, we will do it in one clock step. So there will be many small basic blocks which will very quickly complete its operations and just sit, because of this big basic block takes just one clock cycle, and hence the length of the clock cycle has to be big so that all these operations can be executed within this one clock cycle, and many basic blocks will sit idle after completing all its operations. And hence it is not advisable that you do many operations within one clock step. There is a trade-off which we need to have. So because we are not scheduling all operations using a single clock step, we are dividing the operations within a basic block into separate clock steps, then we have this problem of scheduling. So we have to appropriately schedule different operations into different clock steps. So execute a basic block using separate clock cycles, and that will require scheduling. Chaining is another concept where, let us say, the propagation delay of a particular operation is very small, and a particular operator, I have a functional unit whose propagation delay is very small. That means it can execute the operations within it very fast, such that I can add, say, multiple number of operations within a single clock cycle. So that is possible, and chaining is the chaining is the way by which we do it. So what is chaining? Multiple operations may be executed in the same clock step if overall propagation delay of all these operations together is less than a clock time. Cycle time, right, is less than a cycle time. So therefore this only complicates the scheduling problem itself. Okay. So what is scheduling as such? The scheduling problem is to assign a start time to each operation in the basic block and generate the controller to direct operations in each time step within the basic block. So what are we doing? We are assigning a time step to each operation in the basic block. This operation can be executed over multiple cycles. So the delay of this operation can be over multiple cycles. So an operation can take 4 clock cycles to complete. That is possible. However, we will be assigning the start time of that operation. So the scheduling will assign a distinct start time to each operation. Okay. Now, how do we do that? We said that within a basic block, we have this code which is sequential and straight line. So therefore, first we obtain a data flow graph for it. The edges in this data flow graph denote data dependencies, and the data flow graph is acyclic. And why is it acyclic? Because there are no loops inside it. So, or only straight line control flow occurs, there are no conditions in it. So what happens is that the data flow graph is a DAG, or it is acyclic, and hence we can have a partial order among its operations. So because it is acyclic, it provides a partial order among its operations. And let us now consider a very small basic block. Let us say x plus y into z less than w plus t. This is our basic block. Now this basic block can be converted into this corresponding data flow graph. So this is within a basic block. The control is outside it. Okay. So the first here we have y into z, x plus y into z. So this is what is happening, w plus t on this side, and the comparison occurring here. So this one is a data flow graph corresponding to this basic block. Now from this control flow graph, we simplify, from this data flow graph, we simplify it a bit to help us in scheduling. Now, first what we see is that the variables, the independent variables, will anyhow be kept in separate registers. But what we particularly need in scheduling, we want to schedule operations in the basic operations at different time steps within a basic block, right? The operations have to be scheduled in different time steps. So what we basically need is the constraints, precedence constraints within the operations themselves. If the data is independent, we are not, it is not very important to us at this stage. So therefore, from this data flow graph, we can obtain an operator constraint graph like this. Here, it is almost same as the data flow graph, but it only shows the operation constraints, not the operator constraints, but the operation constraint graph. So it shows the precedence constraints among the operations. So this is it. So and then we add a source and sink. So data flow graph has a single start point and a single end point. So therefore, I can add a source and sink to it. These are obviously no ops, and we get this operation constraint graph from this corresponding data flow graph. Now, on this operation constraints graph, we will do scheduling. Now, in this particular graph, we have, for the sake of simplicity, we have removed the source and sink nodes, and then we have shown two alternative schedules. So, what we said, the process of scheduling is to assign a time step to each operation in the operation constraint graph. So, it will assign the start time to each operation in the operation constraint graph. So, what do we have? We know the area and execution delay of each functional resource type that is available to us. So this is known at the input of the scheduling problem. So what are the different resource types that we have, and what are the characteristics, what are their characteristics in terms of what will be the area consumed on the floor, expected area that will be consumed on the floor by this resource type, what will be their propagation delays, etc. These are known to us. And given this, we can have multiple options for scheduling. For example, for the previous operation constraint graph, we can have this example shows two alternative schedules. In schedule 1, we see that this has been done in 3 steps. The schedule 1 takes 3 time steps. So T1, T2 and T3. And we see that schedule 2 takes 4 time steps, right? However, so therefore, schedule 1, we can say that schedule 1 has a higher performance than schedule 2, which means that when I make a hardware circuit out of this schedule, if I make a hardware circuit using schedule 1, I will get a faster circuit as compared to schedule 2. However, the area consumed by schedule 1 is also higher with respect to schedule 2. Why? Because here we see that I have to use 2 adder operator resources. 2 adder resources I need. Why? Because the addition is being performed at the same time step in parallel. So these 2 additions cannot be done using the same resource. However, in this one, the 3 addition operations are in 3 distinct time steps. So therefore, the same adder resource can be reused for all these addition operations. So therefore, I can do away with just one adder here, but here this will require 2 adders. Hence, there are trade-offs. And this is a very important trade-off which we say as the area versus delay trade-off. The third important step is allocation and binding. So after the scheduling step, we know that for each operation, what should be the time step at which it should be executed, right? At which it should be started. what is the time step at which the operation should be started. We know that. Now, given that, we do allocation and binding. What is the allocation problem? The allocation problem is this. There may be more than one resource type that can execute an operation. Now I have to allocate actual hardware resources to the operations. I have found out which operation to do in which steps. Now functional units have to be mapped to them. Now let us say that two functional unit types can execute the same operation. Then I have to choose which particular functional unit to use. So there may be more than one resource type that can execute an operation. For example, a ripple carry adder and a carry look ahead adder can both do addition. So the same addition operation can be done by the ripple carry adder and the carry look ahead adder. So we have to select the resource type through the problem, through this aspect of allocation. Then binding comes, where we have to map operations to the functional units. Right? We have to map operations to the functional units. So where what we do is that we actually bind the functional units to the operations in the schedule. Allocation and binding can be looked as global optimization as a global optimization problem considering multiple basic blocks. We'll talk of this later in detail, but what we want to say here is that this is not the only basic block for which we are allocating and binding resources on. Now there are multiple modules and multiple modules, and in each of these modules there are multiple basic blocks which are executing, which may possibly execute concurrently. Now all these in all these ones we will try to maximize the usage of resources. So we want to reuse the resource for as many operations, reuse registers for as many variables, reuse the bus as much as possible. Reuse, right? So this is what we want to do, so that the resource utilization is maximized and that reduces the total area of the circuit. So therefore, this allocation and binding step is may be considered a global problem which considers multiple basic blocks at the same time. Finally, at the last step of the high level synthesis is to build the master controller for a FSM controller for a basic block. Now, because I have attached timing to each of the scheduling steps, I can generate a controller that appropriately activates the functional units and the appropriate select through the appropriate select inputs the correct registers and functional unit at a given time. Now for that we can generate the controller, but that does not end. So now we have the controller for one basic block that has to be inserted into the master controller of the entire module, and finally across modules. So we will have a controller controlling the whole application. Now this will be done in step 4. The FSM controller for a basic block is inserted into the master FSM controller, replacing the state of the basic block. So in the master FSM controller, I have a single state for the basic block. Now this single state will be replaced by the controller itself for the basic block, and the timing of the master controller appropriately adjusted. So with this we come to the end of module 2 of lecture 2.